B minus C times A equals 0, where B and C are m by n matrices and A is invertible. Show that B equals C. Oh, these are matrices. So this 0 is also 0 matrix. And B and C are m by n. So let's try to decode what is here. B minus C times A equals 0. So times. So this is m by n matrix. Okay, subtract means it has to be the same size, m by n. So the difference will be m by n. To multiply A, and they say A is invertible. That means A must be a square matrix. Okay, m by m or n by n. So here, when we subtract, we get m by n. So it has to be n by, because the inner dimensions should match when we multiply. So n by n, square means n by n. Okay, when we subtract m by n, this will be m by n matrix. And multiply means they need to match n by n. And when we multiply, this will be outside. This 0 matrix is in fact by m by n size. Okay, we're just talking about the size, which is not really needed here. And we know that A is invertible. That means A inverse exists. So we can multiply both sides by A inverse. Okay, but A is n by n. So A inverse will be also n by n. Okay, this is m by n. So we can't multiply by n by n because they don't match. And again, when we multiply A times B, or anything A inverse times B, that is not same as B times A inverse. Okay, matrix multiplication is not commutative. We cannot commute like that. So A is here, but we can multiply both sides by A inverse from the right side, because A inverse exists. Okay, multiply both sides, okay, by A inverse in the right, from the right side. So this will be B minus C times A. We are multiplying by A inverse, 0 matrix A inverse. But matrix multiplication is associative, so from these two we can group in one. A times A inverse is identity matrix. So this is B minus C times identity matrix. I'm just writing I equals 0 times any matrix is, it's a 0 matrix. Okay, it will be a 0 matrix. And identity times any matrix is that matrix. It's like 1 in number system. So this will be B minus C equals 0 matrix. Now we can add C both sides. That means B equals C. And this is what we are asked to show. Okay, little bit of manipulation and we are there. Another problem here, suppose A is invertible, that means A inverse exists. Show that A inverse is same as this one, or AT transpose. We know that when A is invertible, A transpose is also invertible. Okay. That means A transpose inverse also exists. And when A is invertible, A times AT is also invertible. Okay, we need to show A inverse equals this one. Let's work from right side, because we can manipulate right side and get left side. Right side is A transpose times A inverse times A transpose. And we know that when we distribute this inverse, like when we know that A times B, two matrices, times raised to -1, okay, inverse of a product will be product of inverses in reverse order, by the way, B inverse, A inverse. Okay, that's the fact we learned in class. So this one will be then A inverse times A transpose inverse, and we have A transpose. Okay, matrix multiplication is associative. So there are three. We can now consider the last two product first. Okay, A transpose, okay, times A transpose inverse. What is that? I mean, when A transpose is a matrix, okay? When you have a matrix, let's say M, and if you have M inverse times M, that will be just identity matrix. If you multiply a matrix by its inverse, we get identity matrix. Okay, that's the definition of being inverse. So AT inverse times AT, that will be just I. So this is A inverse times I. I means identity matrix. It's like 1, okay? And identity matrix times A inverse, or identity matrix times any matrix, is just that matrix. It's like multiplying by 1. That's A inverse. And that is in the left side. So this is how we can manipulate more complicated side and get to the easier side. Okay, final. That's the proof.